Welcome back. Let's take a look at a couple special applications of stoichiometry. So one of them is percent yield. So percent yield is our ratio of our actual yield to our theoretical yield. So what's the actual yield? As the name implies, is the amount of product that we actually produce. In an exam question, you'd probably be given this amount right here. And the theoretical yield is how much we would produce if our reaction was 100% efficient. In an exam question, you'd quite likely be asked to calculate this theoretical yield. If we do stoichiometry, that's what we use to find the theoretical yield. So actual over theoretical times 100 gives us that percent yield. So here is an example problem. What is the percent yield if a reaction of 50.0 grams of lithium hydroxide gives 72.8 grams of lithium bicarbonate? So here's our balanced equation. Everything reacts in this particular case in a 1:1:1 ratio. And so we're going to use our molar mass balanced equation, molar mass, just like before. So grams of lithium hydroxide, there's our molar mass, 1:1 ratio from balanced equation, and then our molar mass of our lithium bicarbonate. And we end up with 142 grams of lithium bicarbonate. So this is our theoretical yield. Again, with stoichiometry, we calculate how much we'd produce if our reaction worked perfectly and there was no waste or loss or anything like that. So now we're going to plug it into our percent yield equation. 72.8 grams of lithium bicarbonate, so that was specified in the problem. That's our actual yield, divided by 142 grams of lithium bicarbonate, which is the theoretical yield we calculated using stoichiometry, times 100. Gives us a percent yield of 51.3%. So this reaction is only about half efficient, just over half efficient. We didn't produce nearly as much of the product as we could have if our reaction was 100% efficient. So please pause the video and complete question number 4. Welcome back, everybody. Let's talk about the very last topic in here, the very last special application of stoichiometry. We're going to use it to calculate heat of reaction. But before we do that, we have to talk about heat of reaction. So we have what's called exothermic reactions, and this means that our reactants are higher in potential energy than our products, and when the reaction occurs, then that potential energy is going to leave in the form of kinetic energy. It's going to leave in the form of heat. So imagine we have a big boulder on top of the hill, and we tumble that thing down the hill. It's got high potential energy here. When it tumbles down the hill, it's going to convert that potential energy into kinetic energy. It's motion as it rolls down the hill. Similar idea here, but the type of kinetic energy we see in chemical reactions is usually going to be heat. And so we have an example here. If we take carbon and we combust it with oxygen, we produce CO2, and we also release 394 kilojoules of energy. So one way to express that is to write it as a product on the product side of our equation here. Or people refer to delta H, which means our change in heat. And if we write it this way, people often use a negative sign to specify the direction of that heat. So that's our heat leaving in this case. So we've released 394 kilojoules of heat for every mole of carbon that we combust. So endothermic reactions are the opposite. So we start out with reactants that are low in potential energy. Then we have to add in energy to end up with high potential energy products. So where does that added energy come from? Well, we actually absorb heat in this type of reaction. So here's an example. N2 plus O2 produce NO. So we produce 2 NO here. And notice that our heat in this case is listed as a reactant rather than a product. And the delta H here is expressed as a positive value rather than a negative value, indicating that heat's entering the reaction rather than leaving the reaction. So here's an example problem. If 15.0 grams of NO are produced according to the reaction below, how many kilojoules of energy or kilojoules of heat were absorbed? So this is solved basically like a regular old stoichiometry problem. So 15 grams of NO, then we use our molar mass. So it's 30 grams of NO for every 1 mole, so grams of NO cancel. And now for our equation, for every 2 moles of NO that we produce, we're going to absorb or take 180 kilojoules of energy. So 180 kilojoules for every 2 moles. So this is essentially from our balanced equation. And we end up with 45 kilojoules of heat being absorbed by this reaction. And here we have another example problem. This one is exothermic. If we burn methane with oxygen, we produce CO2, water, and 213 kilojoules of heat. And so we want to figure out how many grams of oxygen were reacted if 306 kilojoules of heat were released. So we start out with the 306 kilojoules, and then using our balanced equation, for every 2 moles of oxygen that we consume, we are going to release 213 kilojoules of heat, so 213 down here, and 2 moles of the O2 from our balanced equation. And then finally our molar mass, 32.0 grams of O2 for every 1 mole, 2 times the 16 in the periodic table because there's 2 oxygen atoms in every O2 molecule. And crunching all our numbers, we end up with 91.9 grams of O2 being consumed. So congratulations, you made it to the end of this video. I'd like you to please pause the video and complete question number 5 on the activity. And again, I urge you to participate in the discussion section of Canvas, ask your questions, help your classmates there, and also get those easy points you get from that discussion board. Bye.